And so to then build a binomial family generalized linear model, we're going to do the same stuff that we've done before. Use the GLM function, specify PA, presence absence, as a function of depth for the Nelson data, and make sure we specify a family argument as well. Now in this case, because it's a binomial generalized linear model, we want a binomial family argument specified in here. This is telling the GLM function that our residuals, our error estimates, are binomially distributed, right? Those points around our model fit, the stochastic part of our model, are binomially distributed. We also need to specify the link function, and in this case, it's something a little bit different than what we've seen before. Now we're dealing with a logit link function. A logit is a type of function that's mathematically actually kind of complex, but what it does basically is it takes zeros and ones and extends them out, right? Just like we did with our kind of log transformation. Let's pull up the qlogis, which is the logit function of 0. If I run this, we get negative infinity, right? What's the logit then of 1? Positive infinity, right? So a logit function, which is in R, you can run the logit function using qlogis. The logit function takes zeros and makes them negative infinity. It takes ones and makes them positive infinity, and it therefore allows our linear model to kind of fit to these data. As kind of normal, you can inspect the diagnostic plots if you really want to. They're really not going to show us much that we don't already know, right? We know that our data are not normally distributed. We know that our residuals are binomially distributed, and then we've got a logit link on the model. And so these diagnostic plots really don't mean quite the same thing that they do when we're dealing with LM functions. You can still look at them if you're curious about independence of residuals and perhaps weird other patterns in the data like that, but it's really not that useful once we've now gone this far into making GLMs. And so with our model, type3.mod, we've got it called, we can pull up, did I not define it? We can pull up the summary. And we can see in the summary, again, same as before, all the familiar pieces. We've got our coefficient estimates. We've got the intercept, beta naught, saying that it's 3.87. We've got the depth coefficient, beta 1, saying that it's negative 0.87. And of course, we need to remember that because we're using a GLM, and we said that the link function of this GLM is a logit link function, that these values are not on the response scale. They're not in a real-world scale. We need to use the inverse logit function to get them back into the real world, because right now they're in logit space, right? And the inverse logit function is, in R, at least p-logis. So for example, if we specified the first coefficient of this model, the intercept, and the p-logis of it, if you just look at the summary output, right, it says the intercept is 3.879, but in real-world units, it's actually 0.98, right? This means that when depth is equal to 0, when our predictor variable is equal to 0, there is a 97.97% chance of finding a type 3 piece of pottery, right? The probability is 0.9797 at a depth of 0. And so if we wanted to then predict this for other depths, right, you do the same thing. You just add your coefficient, take the second coefficient then, which is beta 1, or the slope, and you can multiply it by whatever. If we wanted to predict a depth of 5 feet, we multiply that coefficient 2, beta 1, times 5, add it to our intercept, and then after we add all that stuff together, we then take the p-logis of it, and we get 0.387, right? Probability of a type 3 ceramic being found at a depth of 5 feet is 38.7%, roughly. Now, doing this by hand, right, is one way to do it, of course, and it requires you to know that the p-logis function is the inverse logit function. And you can also just use the predict function like we always do. Type 3 mod, your new data object, your new data argument needs to be a data frame with depth, and we're trying to predict a depth of 5, right? So we also want it on the response scale, which is going to tell it to apply that inverse logit function to the value it's predicting. And again, we get the same thing, a 38.7% chance. So this predict function makes it easy as long as you can remember that it takes a data frame with a labeled column the same as your predictor variable. It has to be the same name. And so this is kind of how the coefficients are working. And of course, what we need to do then, because there's no model summary p-value or r-squared value or anything like that, we got to calculate those ourselves. So again, we use the LM test package, and specifically the LR test function within it, and we run that on our model, and it tells us our model p-value. All right, comparing our model to an intercept-only version, our model PA is a function of depth, to an intercept-only model, PA is a function of 1. That's only the intercept, so there's no slope. We get a chi-squared statistic of 6.35. Degrees of freedom is 1 because there's one fewer parameter in an intercept model than ours. And our p-value is 0.0117, significant at the 0.05 alpha level. And so our result here is unlikely if the null hypothesis of that intercept-only model were true. Now we've got a significant p-value for the model. We report the chi-squared and the degrees of freedom as well. And we can also then use the mod eva package, and specifically the d-squared function within it, and feed that our model, and we get the GLM version of an r-squared, a d-squared, which is, in this case, 0.472. And so what this d-squared statistic means is that 47.2% of the deviance in this kind of model is explained by including depth in the model. So depth is actually doing a pretty good job. That's a moderately strong, nearly moderately strong d-squared value. For archaeological data, that's pretty good, especially with only 10 data points here. So depth has definitely got something to do with what's going on with the presence-absence of these type 3 ceramics. So we've got a significant model, we've got a good d-squared value. We would report saying something like a likelihood ratio test reveals that our model is significant. We would report the chi-squared is equal to, what was it, 6.35. Degrees of freedom is equal to 1. The p is less than 0.05. And we can also say that there is a moderately strong relationship between the probability of type 3 ceramic recovery and depth, and cite our d-squared statistic of 0.47 as such. You could even say something like including depth in our model accounts for 47% of the residual deviance. And so yeah, this is a pretty nice binomial family GLM explaining what's going on with the presence or absence of a certain type of ceramic, which in the modeling context translates to a probability of finding one of those pieces of pottery as a function of depth, which is pretty cool.